You know, when we think about today's AI supercomputers, we're talking about these modern marvels, right? They connect hundreds of thousands, sometimes even millions of processors into one single massive fabric. But there's a hidden fragility inside all that scale, a kind of constant storm of tiny, tiny errors that threatens to bring these absolute giants to their knees. So let's dig into why that is.
This quote just cuts right to the heart of the whole problem. This isn't about the quality of the hardware getting worse or anything like that. No, it's just a statistical inevitability. I mean, think about it. When you have a million of anything, even the most ridiculously rare failures are going to start happening all the time.
So what is this guaranteed failure we're talking about? Well, it has a name that sounds almost trivial, kind of harmless, but its effects are anything but. We're talking about a phenomenon called link flapping.
Now, the key word to latch onto here is transient. A link flap isn't a dead cable or a fried chip. It's more like a momentary flicker, you know? A temporary glitch where the connection just stutters for a second and then it recovers, all on its own. It's not permanently broken, just unstable for a moment.
And what's really wild are the causes. They're surprisingly mundane. We're not talking about some exotic, catastrophic failure. We're talking about stuff like a speck of dust on a connector, a tiny change in temperature, or even just vibrations from the cooling system. These are everyday physical issues that are basically impossible to get rid of completely, especially when you're talking about a massive data center.
And this is what turns those mundane issues into a total catastrophe. This simple formula here, it's brutal. It basically says that the time between flaps in a whole cluster is roughly the time between flaps for a single link, divided by the number of links you have. So let's say one link flaps once every 10 years. Well, in a million-link cluster, you're going to see a flap every 5 minutes. At that scale, the exception becomes the rule. It's constant.
So, for years, the industry has been trying to solve this by building better, cleaner, more perfect hardware. But what if that's the wrong approach entirely? What if the problem isn't actually physical, but logical?
No, really, let's just pause and think about this question for a second. We've been chasing physical perfection, spending fortunes on it. But maybe, just maybe, the real issue is in the rules of communication that we built on top of that messy, imperfect physical world.
And right here, you can see the fundamental mismatch. On one side, you have physical reality. It's analog, it's messy, it's unpredictable. But on the other side, you have our network protocols, like TCP/IP, that run basically the entire internet. And they're built on this beautiful lie, that the world is digital, discrete, and perfectly ordered. They just assume success, and they really don't know how to handle uncertainty.
And this is the absolute crucial point. When a link flaps, the protocol has no idea if the data got there or not. It's stuck in this state of uncertainty. But because it doesn't have a word for "I don't know," it defaults to the only thing it does know: failure. It panics.
And that panic creates this absolutely catastrophic failure loop. It starts with a tiny physical flicker that creates uncertainty. Then the protocol's timeout goes off, assuming the absolute worst, so it starts retrying, flooding the network with even more traffic. This extra noise can actually make the instability worse, leading to a full link reset, which often crashes an entire multi-million-dollar AI training job. A tiny little problem gets amplified into a total system failure.
So, if the old rulebook is the problem, then we need a new one. And this brings us to a fundamentally different way of thinking, called Open Atomic Ethernet, or OAE. And this isn't just an update, it's a complete rethinking of what a network's job even is. This quote from Paul Baril, one of the key people behind this work, just sums up the mission perfectly. OAE gets rid of the guessing game. No more waiting for a timeout and just hoping a retry will work. Instead, it seeks definitive knowledge, right there, directly at the link. This really shows the core philosophical shift. The old way is probabilistic. It tries its best, best effort delivery and just hopes for success. OA is deterministic. Its main principle is that a transfer isn't real until it is known to be real. It operates on certainty, not on assumption.
So how does it get this certainty? Well, one of the key ideas is called triangle supervision. Imagine you and a friend are yelling across a canyon. If you yell something and don't hear a reply, you have no idea. Did they not hear you? Or did they reply and you just didn't hear them? But what if a third person was on a nearby cliff? They could see both of you and confirm, yep, he heard you, he's just thinking. That's basically what OAE does. It uses a third neighboring node as a kind of referee to turn that ambiguity into a known state, all without any guessing or timeout.
And all of this leads to a really simple but incredibly powerful outcome. Under OAE, when a link flaps, it doesn't cause a system-wide panic. The system just pauses progress on that one specific link until things are stable again. The failure is contained. It doesn't spread upwards and crash the whole application. The recovery is kept completely local.
Okay, so we have this new foundation, this new rulebook. What does it actually mean in practice? Well, the implications are profound. It fundamentally changes the nature of these large-scale systems, from being incredibly fragile to incredibly resilient. This right here, this is the single biggest takeaway. With OEE, a link flap is no longer a fatal error that crashes your entire system. It just becomes a temporary performance dip. The system might slow down for a moment, sure, but it doesn't lose data, it doesn't crash, the job keeps on running. This is an absolute game changer. And look, this isn't just some theoretical problem for giant companies. Check out this data from EXO, a project that links multiple Macs together to run big AI models. See that? For a single task, adding more computers actually slows it down. That's network overhead, the cost of all that communication becoming a bottleneck. This is exactly the kind of inefficiency that a more deterministic protocol like OAA is designed to eliminate at its very root.
And that's really where we are today. We've gotten incredibly good at the physics of sending light down a fiber optic cable. The problem has moved up the stack. It's not about the hardware anymore. It's about the outdated, assumption-filled rules we're using to interpret what that hardware is doing.
And that leads to this final, much bigger question. I mean, this is about way more than just fixing link flaps in AI clusters. If we build our entire digital world on a foundation that guarantees knowledge instead of just making a best effort, what new kinds of reliable, resilient, and truly massive systems could we create? What else becomes possible?